All right, so today's lesson is the last lesson of topic 3. And we're kind of just tying up some loose ends. So like I told you, the questions on your topic for each test are all kind of stacked together. It'll ask you to make a scatter plot, make a trend line, describe the correlation. Now we're going to add on a few more things to that. So today what we'll be doing is analyzing those trend lines, those lines of fit, and seeing if they're a good or bad fit for the data. So in order to do that, you need to be able to calculate, plot, and analyze residuals to assess the fit of a function. And then we're also going to talk about if an estimate is interpolation versus extrapolation, and also distinguishing between correlation and causation. So all stuff that are describing trend lines still. So other ways to evaluate your data. I am recording now and I'll post it later just like I always do. So if you're absent, make sure that you're watching the videos. And I also have a ton from last year that are also helpful. So use them, don't use them, they're there if you need them. Just I'd rather you have them and not need them than need them and not have them. So there they are. Then you do have a practice. Now today we probably won't have time in class to work on the practice, but I will set aside time on a different day for you to work on your practice and on your exit tickets that goes with this. So just be aware, after today's lesson, you should be able to do the whole thing, but we will set aside some class time to do that and the exit ticket. And I know I gave you a lot of papers today. One of them is the topic 3 test review. So the packet is your study guide. It looks just like the actual test, just different numbers, different situations. And you'll see when you go through it that, again, all the problems relate to each other. At least towards the end they do. Now, I'm perfectly aware that some of you have MATLAB and you guys go through it, which I think is great. And just like last time, I do offer some extra credit for completing it and turning it in. But what I look for when I'm giving extra credit is not for you just to copy down the answer that Ms. Knight or Ms. Bowers tell you. All right, that does nothing, in my opinion, for you on the test. Unless you can actually show work or provide an explanation for the ones that you can't show work on, that's what I'll look for when I'm rewarding extra credit for that. So don't just focus on, okay, for this review, the number 1 is C or something like that, because it's going to be different numbers on your test. I need you to know why number 1 is C and things like that. Questions about it? All right. So then also I need to tell you, we did have to adjust the assessment schedule because we are doing benchmarks tomorrow and Friday. So I know I told you that we would be testing topic 3 on Friday. We're moving that to next week. So be ready to take that test on Tuesday, which maybe that works in your favor. It does give you like about 6 extra days, including the weekend, to study and prepare. So use that time, work on your study guide, ask me questions, but we're taking benchmarks tomorrow and Friday. Any questions? All right, and then I'll talk more about benchmarks and how you're scored on those tomorrow. We have 2 days, so I think I can just briefly tell you how you'll be scored tomorrow. All right, but let's go ahead and jump into the lesson. So first thing we're going to talk about is analyzing your trend lines. So I have this paper in front of you. All right, so first thing you need to know, or first new thing that you're going to learn today, is a residual. All right, a residual is the difference between your observed Y value or your actual Y value and the predicted Y value. It is the vertical distance. That says vertical distance from the actual plotted point to the point on the regression line. So the formula, which is here, and like you do get to use your notes on the exit ticket and on your first attempt at the test, not on your retake. But the formula is not hard to remember or hard to find if you're doing your exit ticket or the first attempt of the test. It's the actual value minus the predicted value. I kind of think of it as like A comes first in the alphabet. So I always know that it's actual minus predicted. The hard part, I guess, is remembering which one is your actual and which one is your predicted. All right, I'm more like science brain, so we do these a lot. The way I think of it, it's like actual is the actual data you collected that you saw with your own eyes. So that would be from your scatter plot. So actual is from your scatter plot. Or data table. And your predicted is from your line of fit. And then here's a visual for you. All right, here's a scatter plot, and they estimated a line of fit that goes to the middle of the data. And the actual minus the predicted. So let's see that. These points are both for when the x value is what? So when x is 4, we have the actual value, which is equal to what? So what's the output for the actual value? 3. So my actual value is 3. My predicted value is what? 5. And it's the vertical distance between them. It's actual minus predicted. So my residual in this example is 3 minus 5, which is -2. All right, that's how you would calculate residuals. I'm measuring from the actual to the predicted. And looking at it, the distribution or even just looking at the numbers can tell you how well the data fits, like how well the line fits the data. And residuals that are closer to 0 would indicate a better fit. Because wouldn't that mean that it's right on the line if the residual is 0? Because that means there's no distance between the actual and the predicted. So we want our residuals to be as close to 0 as possible for our trend lines. Questions there? All right, so then let's do like a real world example. So one where they actually collected data from. So we're going to use residuals to calculate the quality of fit for this line. So they already estimated the trend line, just like how we did yesterday. They say that this trend line should help us predict other data. And Y represents median age, and X is year since 1970. So it looks like they conducted a survey. X is year since 1970. So here's the raw data, and then they converted it to a table. Why did the X change from 1970 to 0?
Because X is years since 1970.
Good, because we changed it so that X is year since 1970. How many years is 1970 from 1970? 0. What about from 1980? And then keep going, 1990. So that's how they're making the table. I know on your test, you do kind of have to do some math like that sometimes. Like if it's asking you, and this is unrelated to this example, but if it's asking you to solve for the output, if Pablo worked from 4 p.m. to 7:30 p.m., all right, how many hours passed? 3 exactly? Like 3.5 hours, right? So then that would be what you were inputting. So just keep that in mind, like don't overthink it. If X is year since 1970, that's the math that they're doing, that's how we got here. Any questions? All right, I'm gonna say that because this is unrelated to that problem. All right. So now we're going to calculate the residuals. And we have like a nice little table here that can help us. But really all we're doing is actual minus predicted. Now the predicted Y value is what we get from our trend line. So our trend line is Y equals 0.25x plus 29. Here's my inputs, my X's. Here's my actual Y from the data. How do you think we're getting our predicted Y's? From the equation, what are we doing with the equation? Okay. So that was close, we're plugging in the X values only. All right, so we're going to take our equation, which is 0.25 times X with our first X value, plus 29, and calculating that. What do we get? We get 29 for our first predicted Y value. And then do the same thing with the next one. Plug it into your equation. You get 0.25 times 10 plus 29. This time I'll use a calculator. And we get 31.5. All right, so do the same thing with the other X values. So practice inputting these other X values into the equation to get your predicted Y values. Your predicted Y values come from your line of fit. So your setup should have looked like this. We're just plugging in your X values. All right, so what did you get for the predicted Y value when X is 20? 35? All right, I got 34. So double check that one. What about when X is 30? 36.5. And when X is 40? 39. Anyone confused how we got those? All right, so again, these are our predicted Y values. So predicted Y, it's really just these N numbers here. All right, we showed you the work so that way you can make those connections, but it's really just these numbers that I'm highlighting in green. And then your actual is what they got when they did the survey. So I'll just highlight those in blue. All right, your residual is always your actual minus your predicted. So what was my actual for the first row? My actual was 29.2. My predicted was what? 29. So we're subtracting them. So what's my residual for that one?
0.
Good. 0.2. And then keep going. We had our actual, which was minus your predicted, which is, and what's my residual on that one? This time it's a negative 0.2. So practice calculating these last three on your own, and we'll see if you're right. All right, so what did you get for the residual when X is 20? 0, good. Because the actual and the predicted y value were the exact same number. Is that good? Does that mean that the trend line's good? Yes, if they could all be 0, it would be perfect. All right, but usually it's not perfect, usually it's just close to 0. What about when x is 30? And then when x is 40? Negative 0.8. So then when I'm looking at my residuals, are all of them pretty close to 0? So would you say that this trend line that they estimated is a good fit for the data? Yes. In that case, you can use it to predict other things or maybe make decisions. Like if you were using this in your business to calculate like sales and stuff, maybe it could help you to decide things like that. Right? And making a table is a good strategy. I mean, do you really need to show all of this? No, but at least it'll help you make those connections on your test. Right? Your actual minus your predicted. Questions? All right. Now, another way that you can use your residuals to determine your effectiveness of your line of fit is to plot them. So you should have all this written down. Sometimes you'll see a residual plot like this one that you can graph your residuals on. So we're going to be plotting, so 0 was our x, so our x's, and then whatever the residual value was. So what was my residual for when x is 0? Look on the other side of your paper. What was my residual for when x is 0? We just calculated it. 0.2, right? So when x is 0, my residual is 0.2. So that's what we are going to plot. Along with all of our other residuals. What about when x is 10? What was our residual? Negative 0.2. When x is 20. When x is 30. And when x is 40. Negative 0.8. So then plot these points on your residual plot. So like 0 and 0.2 would be here. 10, because your x-axis is here. And negative 0.2 would be here. And then plot your other ones. Right, and then compare your plot to mine. Right, this is how it looks like plotted. And would you say that this plot is like tightly distributed around the 0? So like 0's here. Are they all pretty close to 0? Yes, even this one that's down here, that value is negative 0.8. Isn't that pretty close to 0? So when you see that it's tightly distributed around the 0, and that you have some data above, below, and on the line, that's a really good fit. If they were like far away, or if these values were a lot bigger, maybe like -5 or like +5, things like that, maybe there's a better line of fit out there than the one that was used. All right, questions? So normally I would have you guys try a problem yourself from start to finish, but I'm also going to show you something that I think would be helpful, which is learning how to use it with, say, like a graphing calculator. And I know all of you might have like different types of calculators, so I'm going to show you all using Desmos since you all have access to Desmos on your Chromebooks. So take out your Chromebooks. And while you guys, estimated and plotted your residuals by hand, most of the time, scientists don't do that. Right? They usually plot it with a computer. With your graphing calculator, it's like having your own little computer. So take out your Chromebooks, and we are going to open up Desmos. And go on the graphing calculator versus the scientific calculator. I'm going to go back to the data table that it gave me, the one here in pink on my screen. Because what you can do on Desmos is you can press this little plus sign. Everyone see it? Press it. So do it as I'm doing it so that you can get that muscle memory. Hit the plus sign, and I'm going to put in a table. All right, and I get this little XY table here. I have an XY table from the problem. So I'm going to put those values in this table. So we have 0, 29.2, 10, 31.3, and then keep going till it matches the table that you were given in the problem. All right, so again, if you missed that first part, use the plus sign, hit table, and we're just copying over the points from the problem, from our paper. All right, now here's the cool part. So if you zoom out to where those points actually are, it makes a nice little scatter plot for you. What's the correlation of that scatter plot? Positive. Would you say that it's strong? Yes, because they do look like they would fall in a straight line. But look what else Desmos can do for you. And you'll probably want to write this like in your notes, like maybe in the free space here, like directions for Desmos. Because even sometimes I forget how to type this in and I have to like look it up. But what you're typing in is basically y equals mx plus b. But you're typing it so that the graphing calculator can read it. So it's y1, squiggly line. It's like above your tab button. That's what my computer is. Then mx1 plus b. All right, so maybe write down what I typed, and then you do the same thing. All right, what it gives you is a trend line. And graphing calculators, they don't really estimate trend lines. They give you like the best one that they can compute. So this can help you confirm a lot of your answers on your test. Because if it's asking you to estimate the R value, your correlation coefficient, if it's a strong positive, what should it be close to? So remember the R values, I'm not talking about the residual, I'm talking about the correlation coefficient from the past 2 days. When it's a strong positive, what is that R value close to? Close to a positive what? Which it tells you down here in this little bit of information. You see that? It estimates your R value for you. Would you say that that R value is close to 1? Yes. Above that is an R squared value, which that is for your residuals. All right, so the lesson that we did today on residuals, that R squared value being close to 0 will tell you if it's a good fit. So would you say that 0.995 is close to 0? Yes, so we're talking about residuals, yes. When we're talking about R's, the correlation coefficient, it just goes from -1 to 1. So we want that to be as close to 1 as possible. But also look here. You see where it says residuals and plot? Press that button. And then look at what happens to your table. Of course, it gives you the residuals, which is nice. These are my residuals. But then it also plots them on my graph. in the red. Everyone see that, or at least on their own screen? And then would you say that all these points are like tightly around the x-axis? So would that be a good or a bad fit? It would be a good fit. So that's how you can confirm some of your answers. And then down here, it also has an estimate for your slope and your y-intercept. So if you're also told to estimate your trend line, you can use that. You can pick the answer option that has a slope close to 0.23 and a y-intercept close to 29. All right, so tons of helpful stuff here. It's just a matter of knowing how to use it. So that's why I make sure you write this formula in your notes. Questions? All right, so that, and I'll show you, will help you answer a ton of questions on your test. So like I pulled up and I pasted it into the smartboard, some questions from your test. All right, it's not on your paper or anything, it's just on my screen. And I also whited out some stuff so that you can't cheat, right? But these are the questions they're asking you. To compute the residuals for the trend line. So you have to put the x values and the residual values. What's the formula for residuals? Actual minus predicted. So do that. And then this one's more like a problem from yesterday, but it says in item 12, so like I said, all the questions relate back to each other. In item 12, estimate the time it'll take Yumiko to run blank miles. So I whited out how many miles, but you would plug that into your equation and solve. Number 18 is what we'll figure out right now, interpolation versus extrapolation. And then we'll do 20 later too. But any questions so far? Sorry if it feels like we're taking a lot of notes. It's just like the loose ends that we need to tie up. All right, so now look at this part on your note sheet. So on your residuals note sheet, look at extrapolation versus interpolation. That just tells us if the data points that we're predicting fall within the range of data or outside the range of data. So if it falls within the range of data, that's interpolation. If it falls outside the range of data, that's extrapolation. All right, and the way I think about it, so it's within the range or inside the range is interpolation. If it's outside the range or extra of the range, then it's extrapolation. So like, here's some examples. Here's our graph with a trend line attached to it. And it says estimate the value for y when x is 1.5. So 1.5 for x would be about right here, like this tick mark. It doesn't have a data point for it though, does it? Like from the scatter plot. It just has a trend line. It would be like right here. Would you say that that is within the range of data or outside the range of data? Within, because look at my data. It goes from 0 to what? It goes from 0 to 3. So 1.5 falls inside of that range. So is that interpolation or extrapolation? Interpolation. That's an example of interpolation. What about over here when we're estimating when x is 3.5? Is that in the range or outside the range of data? So remember, our data goes from 0 to 3. So 3.5, is that between 0 and 3 or outside 0 and 3? So that would be extrapolation. Make sense? All right. If it did ask you to actually estimate it, right now it just wants us to classify it. It's easy because you have the trend line. You don't necessarily need the equation, you can just use the line. So when x is 1.5, what's that y value expected to be? If it's on this line. So read the graph. When x is 1.5, what's my y value? It's near 2.5. So you can use your trend line to estimate other data points that you didn't necessarily collect. What about over here? When x is 3.5, so that would be in between here. So if I'm following the line, it would be about up here. What's my y value expected to be? Near 4.5. Questions? All right, so then try the bottom two. Tell me if it's extrapolation or interpolation. And then maybe like a bonus, you can estimate the y value. So it's asking you to estimate for when x is 6. So is that within the range or outside the range? So my data goes from 2 to 8. 6 is in between that, right? So it should be interpolation. It falls within the range of data. Did anyone actually estimate the y? Because remember, they should be like in a straight line. I know the trend line isn't drawn for you this time, but they should line up. If you estimated it, I think a good estimate would be like around here. So maybe like 4.5, or maybe 4. Again, it's just an estimate. Questions there? Now for when x is 10, would that be interpolation or extrapolation? Why extrapolation? Good. Range goes from 2 to 8. So 10 is outside that range. And if you estimated it, what did you say? Which would be like 0 or like maybe even negative if they have negatives. Questions? All right. And then I know someone in the last class, they actually used Desmos for the scatter plots. They just plotted all the points in their table and then made a trend line and estimated it that way. All right, so again, use it as long as you get the right answer. I'm not mad that you use it properly. All right, now on your practice, it talks a little bit about correlation and causation, but that's a pretty quick, easy lesson. So I know it feels like we're taking a lot of notes. It's just like real quick and easy. Any questions? All right, so now we're on this paper, correlation and causation. First, let's fill in these blanks. We have causation means a change in one variable results directly from changing the other variable. So it's like proven. I'll give you some examples. But causation is where something directly causes something else. And in that case, it's reasonable to expect the data to show correlation. So if something directly causes something else, I should probably expect there to be either a strong correlation or a negative correlation. If something directly causes something else. But the reverse of that is not true. Just because you observe a correlation between variables does not necessarily mean that the change in one variable caused a change to the other. So just because two things have a relationship doesn't mean that one causes the other. Like I know in the past, one of the students conducted a survey, and there's not supposed to be a correlation between these two things, but there just happened to be a correlation between students' height and the number of siblings that they have. Right? Those don't directly cause each other, but there just happened to be a correlation between them. So just because there's a correlation, that does not mean that there's causation. In fact, it's really hard to prove causation. All right, causation is only proven when there's studies done, over a period of time. And I'll give you some examples. But most of the time, causation is hard to prove. So when you get to those questions on your test, like on number 20 of your test, so does the data show a positive or negative correlation? Can it be used to show causation? Most of the time, it cannot show causation unless it's something proven. So here's an example. Back here. So here's a good example, especially because we live in Arizona. So in the summer, ice cream sales tend to increase, right? Because what do you crave when it's hot outside for a dessert? Ice cream or something cold. Versus in the winter, maybe you crave something else, like pumpkin pie or something that'll warm you up. Not so much ice cream. So I'm actually going to change this a little bit though, because does the sun cause you to more ice cream? No. So I'm going to change this a little bit. It says causation between here. Cross that out and write correlation. Because the sun doesn't make you want to have ice cream. You could want ice cream for other reasons than it's hot outside. Because do they still sell ice cream in the winter?
Yes.
Yes. So that is not causation. That's just correlation. But an example of causation would be that in the summer, sunburns tend to increase. Because what causes sunburns? The sun. Do other things cause sunburns? So that's why this is an example of causation. That makes sense? So very rarely is there causation, but it's been proven the sun causes sunburns and nothing else causes the sunburn. Now, we did say ice cream sales increase in the summer, sunburns increase in the summer. So there is a correlation between the two. If I plotted it on a graph, so ice cream sales and sunburns, and I know sunburns is one word, but I'm going to split it up. And sunburns, the correlation would probably look like this. But does that mean that ice creams cause sunburns?
No.
And does that mean that sunburns make you want to have ice cream? No. There might be a strong relationship there, but that doesn't mean it causes it. Questions about that? All right, so we'll do one example. The example down here is about ice cream sales, which we already talked about, so we're going to do the one on the back. And then I did this one in my other class, and I did like it, but let's do this one together, because I like it. It's about study. All right, it's about educational researchers are investigating the relationship between the number of musical instruments a student plays and a student's grade in math. All right, so those are the two things being compared, is their number of instruments they play and their grade in math. The researchers conducted a survey asking 110 students the number of musical instruments they play and what their grade is in math. The two variables are what? What are the two things being compared? So number of instruments played, the listen, it's on the back of your note sheet. Example C. So number of instruments played and what else? Good. Because there is actual studies out there that say kids that are more, I don't know a good word, but like attracted to music, like they want to play more instruments, things like that, tend to have better grades in math. Like it's a weird study, but it has a strong relationship. In this example, the researchers found that students who play a greater number of musical instruments tend to have a greater average grade in math. It is likely that blank causes an increase in blank. So do you think that the number of instruments played causes an increase in math grade, or that the math grade causes an increase in number of instruments played? All right, good, I would agree. So number of instruments played causes an increase in math grade. Because is the reverse true? Like, do all the kids that have high grades in math play an instrument or play more than one instrument? No. So it is doubtful that math grade causes an increase in number of instruments played. Right. Even though there is a strong, would you say that this is a strong positive or negative correlation? Positive. Right, because they said as one increases, so does the other. So even though this is a strong positive correlation between instruments played and math variables, or not math variables, math grades, sorry, this does not imply what? What is really hard to prove? This does not imply causation. Because there may be other reasons that, what do you think goes there? There may be other reasons that people play instruments. There may be other reasons that people have high grades in math. You can put either one of those in there. I'm going to put because there may be other reasons that students have high math grades. All right, like what are other reasons that students have high math grades? They study, they go to tutoring. Now, does that mean that if you study and go to tutoring, your grades in math is necessarily high?
No.
No. So again, causation is really hard to prove. Questions? All right, but then just to add to that, like usually study does increase math grades. There's a strong correlation there. Does not causation. All right, so that's all I have for you. That gives you like 8 minutes to work on your practice. It's not really due until after benchmarks. So we'll revisit this Monday. You'll practice and we'll do an exit ticket on Monday.